We continue with our determining the solution of the Poisson's flow. We have determined the non-zero term coming out of the continuity equation, and now we try to determine what we get from the momentum equations. And if you write down the equation, then you obtain only this as non-zero terms. The other terms do not contribute anything because of the assumptions that we have made, and the assumptions are already have been described, they have been written down, so we know. So all these values are clearly specified in our discussion only. So the non-zero term coming out of the momentum equation is this, and we have one part coming out of continuity equation. The solution of these two is going to give us the solution of the problem, and therefore we look for it. And this is to be remembered. This is an alert being shown here that remember this problem is being considered for laminar flow. No turbulence is there. These are important assumptions because they have an impact on the solution. So now we have to integrate these equations. And from our momentum equation, the non-zero term that we will get is partial derivative of P by partial derivative of R will be 0. Since dP by dr is equal to 0, the only term, and of course since the motion is axisymmetric, therefore the partial derivative of theta is also vanishing, and therefore we conclude that the only variation in P will take place because of x. And we know that the pressure that is being applied is also with respect to x. Trying to combining these results that we have obtained, and from the momentum equation we obtained this term. And remember that we have here are du by dr, and they are related to P, and we are required to determine both u and P, and of course they will be determined. The unknown here is C1, the constant of integration, and once we substitute the boundary condition values, we are going to get the value of C also. So another integration, or putting it, trying to write it, once we integrate it again, we will have the value of u, and because we have introduced a second integration, then therefore C2, another term, is appearing here. And this is giving us a problem situation now that we have to determine two unknown constants. Both are constants of integration. And how do we determine them? The methodology remains the same. We apply the boundary conditions and then we determine these values. Looking at the geometry, the flow will look like this, because it is obvious that if we have to consider in terms of R, then R is having a square term coming in here. And if R is a square, then the total flow picture, there will be variation, there will be contribution from these terms as well. But the dominating term is this. The motion is generated because of the dP by dx. And therefore, you can see, because of the R square term, the flow looks like parabolic. You can see that it is axisymmetric, no gravity playing any role, and U is only dependent on R. So as R changes, that is, as the radius of this pipe changes, the value of U also changes. It has a maximum value at the center, where R is equal to 0. and minimum values at the boundary of the pipe where R is equal to capital R, and because when it is at the boundary point, then the viscosity comes into effect, and because of viscosity, the fluid which is in touch with the boundary of the pipe will have a zero value. It has a no slip condition and therefore no flow coming out of it. The force that is pushing the fluid is dP by dx, the external pressure that is being applied. Therefore, it is important to note down that the main term in our solution that is dominating is R. dP by dx is the applied pressure gradient, so in a way this is given in the problem, and the only thing that are varying now is with respect to R. And when we divide it throughout by R and again integrate it, because we have to determine the value of U. So that will eliminate R from here, the differentiation, and we will have a solution. The solution is this, and its geometrical representation is shown here. So that's the solution of the picture, and we have shown a diagram also how the fluid flow looks like.